Leah here from leahforsci.com, and in this video we're going to look at the 3 steps of a radical reaction: initiation, propagation, termination. For even more on radicals, see the link below or visit my website leahforsci.com/radical. Before we go into the reaction itself, what is a radical? A radical is a single or unpaired electron. Think about the molecule water, H2O. We have an oxygen single bound to 2 hydrogen atoms, where every bond is made up of 2 electrons that sit between the oxygen and the hydrogen. On the oxygen atom, we have 2 lone pairs, where we have a pair of electrons and another pair of electrons. And that is key. Electrons need to be in pairs to be stable, whether they're unbound, like the 2 lone pairs on oxygen, or bound like the bond between oxygen and hydrogen. But if an electron is by itself without another electron, it becomes so desperate to find a partner that it will start attacking molecules, making it very, very reactive. And this is why free radicals in the body are so dangerous, because we don't want electrons to just start attacking our cells, our DNA, or anything else. Up to this point, you're used to seeing reactions where the electrons move together. For example, if I have a bond between A and B, and I want to show that bond breaking, you're used to drawing an arrow from the bond to the atom that it'll collapse onto, followed by a yield arrow and the results. Since both of the electrons collapsed onto B, A is left with nothing, and B is left with both electrons together. This is called heterolytic cleavage, where hetero tells us that it's different, lytic is to lyse, and cleavage is to break. The hetero tells us that the 2 atoms do not get the same number of electrons. A got nothing, and B got 2. The mechanism arrow for a heterolytic cleavage has that double hook, where I like to think of it as 1 dot on each of these hooks to represent the 2 electrons that are moving together. In a radical reaction, we have homolytic cleavage, where homo means the same, lytic is to lyse, and cleavage tells us the type of reaction we're doing. To show a homolytic cleavage, you start your arrow at the electron that is going to move, and you draw a single-headed or fishhook arrow, where you can imagine that one point is just a single electron, and then another arrow from the other electron to the other atom, again, 1 electron at a time. Homo, meaning the same, tells us that each of these atoms gets the same number of electrons when the bond is broken. That means A has a single unpaired electron, or a radical, and B has a single unpaired radical electron. Both of these are going to be very reactive, so let's take a look at the steps of a radical reaction. The first step of a radical reaction is called initiation, because we initiate the reaction to create the radicals. Cl2, or chlorine gas, has a single bond between 2 chlorine atoms. If we excite this system by hitting the bond with heat or light, this bond is going to get so excited that the electrons no longer want to hold on to each other, and causes them to break apart through homolytic cleavage, where 1 electron goes to each of the chlorine atoms to give us 2 chlorine radicals. A radical electron is the same size as a regular electron, but to emphasize the radical, I'm going to draw them in bigger so that we can clearly follow them throughout this video. We said that this reaction happens with heat or light, and that's because initiation requires the input of energy. Heat can also be written as a delta or a triangle, and light will often be written as H nu, which looks like HV, and sometimes even a squiggly line to show that it's being hit by radiation. Both heat and light can provide enough energy to excite this bond to form our 2 radicals. The key to recognizing an initiation step is that you have 2 radicals in your product but you have no radicals on your reactant side. The second and most common step in a radical reaction is propagation, which should remind you of the word propagate, which means to happen over and over and over, which is exactly what happens in this step. Say we have a molecule of methane that comes into contact with our chlorine radical. The chlorine radical is so reactive that it's going to attack one of the hydrogen atoms from methane with a single fishhook arrow to grab that hydrogen. But that one radical electron is not enough to create a bond. We need a second electron, and so hydrogen is forced to donate one of its electrons that used to bind it to carbon to form a bond with chlorine. I think of this as getting a dinner invitation where you're told, hey, come over to my house for dinner, but by the way, you have to bring dinner. Hydrogen has to bring that electron, which is fine in terms of creating a bond between hydrogen and chlorine, but that other electron that used to bind carbon to hydrogen is now left alone, and so it'll collapse onto the carbon atom, essentially breaking the bond between carbon and hydrogen. As a result, we now get a methyl radical, which has a carbon bound to 3 hydrogen atoms, and that lone electron sitting as a radical on carbon. What else do we have? The hydrogen atom that was attacked by chlorine still holds on to its green electron, but now it sits in a stable bond between the former pink electron that was the chlorine radical for a stable molecule of HCl. HCl is happy, but the methyl radical is not. And this is the idea behind propagation. Even though we have so few radicals at any given time, a radical attacks a molecule to create another radical. This radical will then attack another molecule to create another radical, which attacks another one to create another and another and another. And this is how we constantly propagate that radical reaction. This is the most common step in a radical mechanism, as we'll see in a moment. But first, the key to recognizing a propagation step within a radical reaction is to recognize that you have just one radical on your reactant side and one radical on your product side. The third step in a radical reaction is termination, where we terminate or destroy the radical. This is not a very common step, as we'll see shortly, but first let's take a look at what happens. The idea with termination is if I have a radical that comes into contact with another radical, the two radicals will reach out, combine their electrons, and form a bond. In this step, we went from having 2 radicals to no radicals, which sounds like a very good step, except for the fact that radicals are not that common. So the chance of a radical running into another radical is very low, but the chance of a radical running into a non-radical for a propagation step is so much higher. When you have a termination reaction, it doesn't matter what the radical is. If a radical meets another radical, we can have termination. In the last 2 steps, we saw the formation of a chlorine radical as well as a methyl radical. Termination will allow us to mix and match any of these radicals as follows. A chlorine radical can meet up with another chlorine radical to give us a molecule of Cl2. A methyl radical can meet up with another methyl radical to give us a longer carbon chain, in this case ethane. And finally, the chlorine radical can run into a methane radical and combine to form chloromethane. The key to recognizing a termination step is to notice that you have 2 radicals on the reactant side and no radicals on the product side. This is often tested, especially on the ACS, so make sure you know what to look out for. Initiation, radicals only on the product side. Propagation, 1 radical in the reactant, 1 in the product. And termination, 2 radicals only in the reactants. Now that you have the steps, let's take a look at the free radical halogenation of methane, specifically radical chlorination. The reaction begins when a molecule of chlorine is hit with heat or light that breaks the bond via homolytic cleavage to give us two Cl radicals. In step 2, the chlorine radical will reach out for and grab a hydrogen atom, forcing hydrogen to provide one of the electrons that binded to carbon to complete that bond, where the second electron collapses back onto carbon. This gives us a stable HCl, but an unstable methyl radical. This is a propagation step. The third step is where I see the most mistakes. We formed two chlorine radicals. We used up one. That means we now have one chlorine radical and one methyl radical, but they will not react with each other. Remember, we have very few radicals, and the chance of one running into the other is very low. Instead, we have another propagation step, where the methyl radical will find another molecule of chlorine and do another propagation reaction, where the methyl radical attacks chlorine. Chlorine is forced to provide one of its electrons to complete that bond, and the other electron from that chlorine bond collapses onto the chlorine atom. This gives us a stable chloromethane and an unstable reactive chlorine radical for another propagation step. And the next step still isn't termination, because this chlorine radical will find another methane to attack like we had here, and this reaction will just propagate and keep going and going and going. And maybe eventually two radicals may run into each other, as we saw here, where two chlorines give us a Cl2, two methyls give us ethane, and maybe a methyl and chlorine come together to give us methyl chloride. But this is primarily how we form the methyl chloride. For even more on radicals, from hybridization, stability, resonance, and reactions, see the link below or visit my website, leiafortsci.com/radical. The link again, leiafortsci.com/radical.